Hi, so I'm going to guide you through this investigation 2, page 387, and this is about coin toss. Yeah. So that's our heading. And to begin with, okay, I'm going to simulate the coin toss in Excel. So we're going to toss a coin 10 times and see what results we get. So to do that, we could set up a formula that gives us a random number. And in Norwegian, it's going to be tilfeldig mellom. Now, in the English version of Excel, that's going to be random between. If you start typing rand, there should be an option random between. So we want a random number between, well, let's say 1 and 2. So either 1 or 2, that's going to be heads or tails. 1, and then the other value is 2. So we want a random number between 1 and 2. And this time it turns out to be 2. Yeah. If you copy this down, let's make sure you have 10 trials. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 trials. Yeah. If you want, you can set up what 1 and 2 is supposed to mean. So let's just write first 10 point, right? And okay, so we could set up if this cell here, and I'll just click it, if B3 turns out to be equal to 1, then this is equivalent to heads. Okay, so 1 means heads. If this is not true, if B3 is something different, oh, thank you. B3 is something different, then this value is going to be tails. So this is the formula you can set up then if you want a description of what these values mean. So 1 is heads, 2 is tails. And since this was a 2, this field here returns the value tails. And you can copy this down as well. And every time you change something, you generate this experiment again to get new values. Now, what we can do now is we can put in a chart. So let's put in bar chart. Let's see, histogram. Yeah, let's try that. Histogram. Nope, it's not the one we wanted. Try this one. Put in histogram like this. Yeah, okay. So this diagram shows us how many heads, how many tails we got. And if I generate the data again, you can see that this changes, right? So the number of heads, the number of tails is going to change for every time you do the experiment. Yeah. So now we want to set up our hypothesis for this experiment. So our H0 hypothesis, that's what we also call the null hypothesis. And you can see the data updates every time we press something here, is that the coin is fair. Okay, so that's a reasonable assumption for our null hypothesis. So that's what we want to test. Yeah? And H1 is what we call the alternative hypothesis, which is that the coin is not fair. Yeah. Now, the first question for this investigation was a bit difficult, I thought, and the main reason why I wanted to go through this with you. So, without doing any calculations, write down a range of values for the number of heads to appear in the 10 tosses that will make you reject the null hypothesis that the coin is fair. So, another way of saying this is how many heads would you accept and still hold on to the null hypothesis that the coin is fair? I mean, how tilted or how biased would this experiment have to be for you to reject the null hypothesis and think that this coin was unfair in some way? So, I mean, if you got 10 heads in a row, you might suspect that there was something strange about this. But so you're not asked to do any calculations here. But I mean, before we make that guess, I'm not sure if we're going to make that guess. I think we'll have a look at the binomial distribution for this experiment. So I'm just going to mark the experiment itself here. So these yellow boxes, that's our coin toss. Yeah. And to set up the binomial probability distribution, we have to do that in GeoGebra. So this is our probability calculator, and this is not a normal distribution, this is a binomial distribution. The parameters we can put in here, we have 10 trials, and we're going to use the probability from our null hypothesis. So question 2 here, use the binomial distribution to work out the probability of the events listed in 1a happening if the coin is fair. So if the coin is fair, that means every time you toss a coin, the probability of heads or tails is going to be 0.5. So there's a 50% chance of each. And by putting in these parameters, this is the probability distribution that you get. I mean, if we look at a single value here, for example, the probability that you get 5 heads and 5 tails, it's not overwhelming. It's about roughly 25% of the experiments. In 25% of these experiments, you would get half of each, right? In 20% of the experiments, you'd get 4 heads and 4 tails, or 4 tails and 6 heads. Yeah. So the next question, do you feel that this probability is small enough that you could reject the null hypothesis if one of the events listed occurred? Let's just pause to take in the question here. Or let's examine properly what this distribution thing means. Up here, this area here, this is the probability that you get 10 heads in a row. this is the probability that you get 1 head and 9 tails. This is 2 heads and 8 tails. This is 3 heads and 7 tails. This is 4 heads and 6 tails. So if I mark this, area here, this is the probability that you get from 3 to 7 heads and the rest are tails. So a 3 to 7 ratio. Yeah. And the probability of that is just under 90%. So that means you have 11% of experiments where you have an 8 to 2 ratio between heads and tails. If we keep expanding this area, we're going to approach what in statistics is called the critical region. So now you can see there's only 2% left of the area, and there's usually a critical value that lies somewhere in between here. So most of the time, you would say that around 5% is usually this critical limit, and we call this a 5% significance level. Sometimes 10% is used. But what this means is we don't usually reject our initial hypothesis unless the result is within this critical 5% area. Now we can copy this this binomial distribution and put this into our investigation here, and we can see that these are the different distributions of the probabilities for 2 heads, 3 heads, 4 heads, 5 heads, 6 heads, and so on. Now, how many would we have to accept and still retain our null hypothesis that the coin is fair? Now, if you set the significance level to 5%, then you would have to accept results where you have 3 heads and 7 tails. But you might not have to accept the results where you have 2 heads and 7 tails. So, I mean, every time we generate a new result here, most of them will be fairly equal, or the difference wouldn't be too great. So here you have 3 and 7, here you have 4 and 6, here you have 6 and 4, here you have 5 and 5, and so on. So you can keep playing around with this, and some of the time you will get results that are outside the critical area. But if you repeat this experiment many times, then you'll find that the majority confirms the null hypothesis that the coin is fair, if indeed this is a fair coin.